Now that we have seen what kind of activation function we can choose in the hidden layers of a network, we are going to see the different types of activation functions we can choose in the output layer of a network. The neurons in the output layer are called output units. Why do we need to distinguish the activation function used in the output layer from the one used in the hidden layers of a network? Contrary to the activation function in the hidden layers, the type of output units depends on the type of the labels in the dataset. Therefore, there are not many possibilities to choose the output units. Let us review the possible choices. If your output is continuous, you must choose a linear output unit. Such units, neurons, compute the classic weighted sum of the inputs and then apply the identity function, leaving the linear combination unchanged. The output can therefore take any possible real values. Note that using a linear output unit and optimizing the network using the square loss is equivalent to solving the least square problem of a linear regression, for which the input variables are the one corresponding to the output of the penultimate layer. In this way, you can see that a network with an output unit performs nothing but a linear regression on new variables, the one provided by the penultimate layer, that are created in a data-driven manner to minimize the squared error. If your output is discrete, you have two different output units you can use depending on the number of categories of the variable. If the variable is binary, you can use a sigmoid output unit, which is again nothing but a classical neuron which computes the weighted sum of the input on which a sigmoid function, the one we have already seen, is applied. Similarly to the linear regression, using a sigmoid output unit is equivalent to applying a logistic regression model on the new features provided by the penultimate layer. Therefore, a network with a sigmoid output unit performs a logistic regression on new features that are automatically created by the penultimate layer of the network. If your output is discrete and have more than two categories, you must use the softmax output units, which is nothing but a generalization of the sigmoid output unit for more than two categories. As you see here, the softmax function takes a vector as input, the linear combination computed by each neuron of the last layer, and transforms it into another vector. This new vector has two characteristics. All components are non-negative and they sum to 1. Therefore, this output vector is a good candidate to be a probability vector. Note that the number of components of this vector equals the number of categories of the output variable, so that the kth component of the vector models the probability of the output being equal to k. The model behind the softmax function is a multinomial logistic regression, which is a generalization of the logistic regression for an output variable with more than two categories. Let us now take a look at the multinomial logistic model. Let us assume that the output y has k different categories. If we perform a logistic regression for each one of these modalities, trying to predict y equal k versus y different from k, we obtain for all k the equation 5, written here for one input variable for simplicity. The right-hand side term is a classical term in a logistic model, and the term on the left is also the classic term where the denominator, usually 1 minus the probability of yi equal k, is replaced by a normalization constant. To determine this constant, we rewrite these equations, obtaining equation 6 for all k. Using the fact that the probabilities must sum to 1, we obtain the value of the constant z in equation 7. Replacing z by its value in equation 6 leads to equation 8, which is exactly the softmax function applied to the vector beta j xi for j ranging from 1 to k. Consequently, you see that the softmax function is the natural function to model probabilities in a multinomial regression model. Now, some comments on the softmax function when used in conjunction with the cross-entropy loss that we are going to detail in a moment. For now, assume that the penultimate layer outputs a vector z associated with a true output y. The cross-entropy loss for this observation is given by minus the logarithm of probability of y equal y given z. If we use a softmax output unit to model the probability, we obtain equation 11, whose two terms correspond to the numerator and the denominator of the softmax function. Now, assuming that one of the components of z is much larger than the other ones, the logarithm of the sum can be well approximated by the maximum of all components of z, which gives equation 12. Based on equation 12, you see that the loss is equal to 0 when the component zy is maximal and much larger than the other components. It means that the network predicts a true label with a large probability. In that case, due to the renormalization present in the softmax function, the component zy is almost equal to 1, and the others are close to 0. Furthermore, still in the case in which the component zy is very large, the loss is approximately linear. There is no saturation phenomenon due to the use of the sigmoid softmax function. Remember that using the cross-entropy loss with a sigmoid softmax output unit is a good idea since it helps to prevent saturation. Lastly, here is a biology analogy about lateral inhibition. Neurons close to each other in the brain may be competing against each other. If the difference in the input signal is too strong between one neuron and the other ones, the first one may activate while the others do not.